Welcome everybody to today's SPREE talk. Today we have Dr. Baran Yildiz. Baran did his PhD here at UNSW with Alistair Sproul as his supervisor. Baran is working with CEEM, the Collaboration on Energy and Environmental Markets, which is a university-wide initiative to engage with behavioural science and finance and business and energy to enable the energy transition. Baran has been working for, I'm going to say nearly a decade in using data to better understand how to integrate more renewables into the grid, looking at voltage disturbances, at curtailment issues, at demand management, and most recently on curtailment and integrated, I can't remember, Cicada. The project's called Cicada, and Baran will tell us about it. It's all about using quality data to improve the integration of renewables. So over to you, Baran.
Thank you so much, Renata, and welcome everyone. Thanks for coming. Today I'll be talking about, as Renata introduced, some strategies to help us with integrating higher levels of consumer energy resources. And some of you will be very familiar with this term, but some others might be working in the device spaces, so I'm going to try to make things as clear as possible with the consumer energy resource concepts. So today's title, Turning Household Water Heating Systems into Megawatt Batteries to Support the Integration of Renewables and Consumer Energy Resources. And let's just start with acknowledgement of the country. I'd like to acknowledge the Bijigal and Gadigal people that are the traditional custodians of this land. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. So today's talk will be informed by two real-world projects. One is through Race for 2030, and the other one sponsored by ARENA. And you can see our industry project partners on this slide. And our research has also been supported by Australian Centre for Advanced Photovoltaics throughout different stages. So thank you to ACAP as well. And we have a wide group of project team working on different aspects, and I really appreciate their work. Most of the outputs today you'll be seeing are from various different project members. So today's content, let's start with the motivation for this. In this area of consumer energy resources, people find these slides very, very familiar. On the left-hand side, we're looking at the ownership of rooftop PV system across different states. And you can see, for example, Queensland estimated percentage of households with PVs over 52%. And we have over 4 million systems in national electricity market now, and the overall percentage of households is more than 40%. So that's very, very impressive. We are leading, the global leader in ownership of rooftop PV systems. On the right-hand side, you can see this famous concept duck curve, increasing rooftop PV exports during the day, and the duck has been gaining weight, as you can see. And in 2024, the net demand goes negative. And I will be giving quite a few examples of this. This curve is from Western Australia, actually from Synergy. So if you look at this slide, and this is from Open Electricity, a wonderful open source tool developed by one of our team members, Dylan. And so with the lights, yellow color, you'll see the generation coming from rooftop solar over the last 12 months period. And rooftop solar has contributed 12.7% to the electricity generation. And we have utility scale solar as well with 7.7%. So overall more than 20% of generation coming from solar only. And we have wind and other renewables. So this is just a little insight what's coming ahead as we have more and more rooftop solar. And this is all great that we have many rooftop solar systems now. And so I'll just share a couple of challenges that is brought by this high level of ownership of rooftop solar. In South Australia, there are various times throughout the year where rooftop solar actually provides the entire electricity demand of the state, and they need to export the excess to the neighboring states through interconnectors. And this can create certain network power system security issues, especially in the events of network disturbances and if the state is islanded. We have worked on various issues regards to rooftop solar and the voltage increases in distribution network, because the voltage rises as more and more rooftop solar exports their electricity in reverse direction. We've done quite a few research in this space, and later comes up, due to these voltage increases, we see rooftop solar being curtailed, the output being reduced, or the systems being completely shut down due to some of the inverter power quality response modes. And this is dictated by Australian standards. And we have worked in this space. We've identified some of the households were losing more than 20% of their generation due to curtailment. And comes in emergency backstop measures. I'm not sure if you're familiar with this term, but this can be thought of as a red button, which is dictated by AEMO, and they can push this button, give signals to various distribution network service provider, and then they would then, through different third-party agents, different communication platforms, can shut down rooftop PV systems in its entirety, especially relevant for the new installed fleet in the last couple of years. And so there are a lot of controversy around this topic. Do we really need this emergency backstop measures? Can we have smarter solutions perhaps to prevent shutting down all of the rooftop fleets of our national electricity market? So these are all the integration challenges that gives motivation to this project. So as we've seen, exports are in some parts of the network creating problems, as well as also benefiting many users in various different ways. Energy storage is an obvious solution to this, right? We can store the excess solar during the day and then use it at other times, perhaps the peak demand periods, to also help networks as well. Now, I've shown in this slide two different types of energy storage. You can see famous Tesla Powerwall, lithium-ion chemical electric storage technology, and we have a thermal storage technology with a 315-liter water storage tank. So now let's just compare these two options. Okay. With Tesla Powerwall, we have around 13.5 kilowatt hours of storage. With, depending on the size of the storage tank, you can have 10 to 15 kilowatt hours of thermal storage, MC delta T, based on the temperature difference between the input temperature and the temperature we use in our houses. Obviously, Tesla Powerwall, you can use it in all electric appliances, whereas the water storage tank is only for water heating application. We have probably $10,000, $11,000 of costs installed, including a $2,000 rebate in New South Wales for a Tesla Powerwall. On the other hand, these water heating systems are $1,000 to $2,000. And in terms of the ownership, Tesla Powerwall, or like other batteries, around 250,000 households own these. Around 4 million households have electric water storage tanks. Typical lifetime, you can see 5 to 8 years for a battery, whereas 10 to 15 years for this thermal storage. And you can see the energy efficiencies as well. Both of them can utilize rooftop solar. So hopefully by the end of this talk, you will be able to identify which one is the low-hanging apple in this instance. So this is the electric versus gas water heating ownership that we could identify, although there is some controversy around these numbers. And also, when you have an electric water heating system, some of these systems may be controlled by your distribution network service providers, or more recently by your retailers or aggregators. So there is also an allocation of whether these systems are controlled or whether it's 24 hours available. Can I get a raise of hands if you have an electric water heating system in your house? This might be resistive heat pump. Okay, great, thank you. Can I get a raise of hands if you have a gas system in your house? Thank you. And so we almost equal allocation, and the percentage changes most of the time. We will get to the comparison of electric versus gas later in this presentation. But an important pointer is around 25% to 30% of total residential energy use is attributed to water heating in Australia. So it's significant potential. The other part of the project is, so at the moment we have around 30 to 40% of ownership of smart meters in households. And Australian Energy Market Operator, AEMC, they project that by 2030, every household in Australia will own a smart meter. So smart meters provide you more granular monitoring of your energy usage. Also, ability to control different circuits in a remote way compared to the old mechanical metering. So now let's bring all of these different components together. We have water heating systems, significant storage potential, and large ownership across Australia. We've mentioned rooftop solar system increasing, and we are the global leader, and smart meters being installed in our households. So this is basically the whole three components of the project. Using smart meters to control electric water heating systems to soak up excess solar in the households as well as in the distribution networks as much as possible. Okay, so now that I've explained the motivation of the project, I'll be sharing some key insights from two real-world trials that we worked on. The one is in South Australia. It's with the metering provider Plus Yes, and the trial was called Flexible Demand Trial. It included around 20,000 households. The other one is within New South Wales with Endeavour Energy. They have worked in Off-Peak Plus trial in the Albion Park neighbourhood, around 10,000 households. And this is just a brief overview of the solution that was developed by Plus Yes for the retailer partner AGL in this trial. Essentially, the metering provider has created an online platform where the retailer can lodge their load control programs, and through the relay management and cloud control, they could turn the water heating system on and off depending on their predetermined schedules and strategies, and they take into account various different variables when controlling these water heating systems. So in this plot, you're looking at the South Australian hot water fleet, and this fleet was divided into 10 different groups. With the darker blue, you see the total demand, and with these various different colors, you're seeing all individual groups and their water heating demands. The dark shaded area with gray, nighttime, and the other white areas are daytime. And what you can see is on some of these control instances, there is a randomization. So the tanks are, rather than being turned on at the same time, they're turning on with a predetermined schedule. This randomization was done 60 minutes initially and then further refined to 30 and 15 minutes. There is also some randomization within each of these control groups. So not all the tanks are turning on at the same time, because we've seen this example in South Australia before. It creates peaks in the network, causing price spikes and different problems. So we've learned the lessons. So we basically organizing different randomization schedules so that we create a smoother demand profile. On the bottom left, you see when there is no randomization. Here, you can see the demand goes above 21 megawatts for this fleet, whereas when there is randomization, it's mostly below 10 megawatts. Now, within this scheduling also, especially during the daytime, there is consideration of wholesale market prices. So the retailer partner is basically trying to optimize these system operations based on the market prices so that they can have more financial benefits. A few summary here. around 20,000 households, and each of these households have a water heating system and electric water heating systems, and they were connected to control loads. So that was the old way of managing these water heating systems through the NSPs. It's a separate designated electrical circuit. What we found out in this trial was around 25% of the households have actually disconnected or moved on to other technologies. So they were not using the control load circuit. So this is a significant finding. And there are reasons for this, because if your water system is being controlled by a third party through a separate electrical circuit, you cannot make use of your own solar directly. And it's actually much more financially beneficial for users to be able to self-consume their solar behind the meter. So people have become aware of this, and they've basically moved from control load circuit to the general supply, where they can actually soak up their solar behind the meter. And throughout this trial, we have tested different control strategies, static, more dynamic, and you can see different percentages of water being shifted to the daytime. On average, 45.5% of water heating demand was shifted to daytime during solar generation periods. And with the most recent strategy, it was around 50%. So half of the water heating demand is being shifted to daytime to soak up solar in the network. At a household level, it's around 1 megawatt hours per year, or 2.5 kilowatt hours per day. And when if we could roll out these strategies across the NEM, we estimate that there is on average 10.5 gigawatt hour of daily flexible hot water demand that can be shifted into solar generation periods. Now let's put this into context. According to recent data from Australian Energy Market Operator, there is an average of 6.3 gigawatt hours of utility scale solar curtailment daily. If we also include wind, it's around 11 gigawatt hours of daily curtailed generation, renewable energy generation, which is practically lost energy. It's also very cheap as well. So you can see this plot from Energy Trends Visualization Project developed by CEEM as well. Here you can look at the curtailed proportion of the utility scale solar farm in South Australia with red, and this is the generation with yellow. So I don't know how I would feel if I was the owner of this solar farm, basically. So there is a really direct match between the shiftable electric demand of hot water versus the daily curtailed generation. So it's actually generation that is lost, and it's practically free. Some solar farms can lose up to 30-40% of their daily generation. And as I mentioned, we estimate around 10.5 gigawatt hours of daily flexible hot water demand that can be easily provided by this lost energy. Now we'll move on to heat pumps. This is becoming more and more popular technology for heating water. Heat pumps, basically like refrigerant cycles, they can utilize the latent heat of ambient air. That way they're more efficient, and their efficiency also changes based on the climate and the temperature. But these systems are being more popular these days. Governments are giving incentives and rebates for heat pumps. What we've seen in this trial, heat pumps also work with these control systems that we've developed, but with one caveat here. Heat pump manufacturers actually do not recommend external control of their systems. They would prefer these units to operate by themselves without someone turning the systems on and off. And there's a reason for it. Their claim is that external control may damage their compressor life cycle. Now that depends from manufacturer to manufacturer, but based on conversations we had with 3 big heat pump manufacturers, that's their view. I would also like to show you some different operational profiles here on heat pump. You can see that the blue one, for example, or the purple one on this plot, heat pumps have much less power consumption compared to resistive systems. They also operate longer periods as well. On the right, there are two frequency distribution plots. And what we would like to show with these is, on the top one, we have assessed what percentage of the resistive systems actually complete their heating operation within the allocated time window. And most of them, you can see, actually uses less than the allowed time window that we have. So most of them complete their heating operations without getting interrupted. On the bottom plot, there are a significant chunk of heat pump operations that actually needs more time than what we've allocated in this trial. So that means they're being interrupted. So that raises some concerns, and there's further work in controlling heat pumps through this smart meter control. I would briefly like to summarize the financial and emissions reduction, financial savings and emissions reduction. We've estimated around $63 per year savings from shifting hot water from nighttime to daytime. And also, this opportunity is likely to grow. We already have lots of free wasted energy in the network. So actually, and it's going to increase as well. So daytime prices are going to get probably lower. That means there is even more motivation. On this plot on the left, the top one, you can see a successful hot water shifting with the red line here, and you can see the overlap of low wholesale market price from that region of South Australia, and this is quite a profitable operation for the retailer. On the bottom plot, on the other hand, the shifted water energy somehow actually aligns with the price peak in the middle of the day. So it's not always foolproof, but generally there is a good amount of financial benefit that can be gained from shifting water demand from nighttime to the daytime where prices are lower. Unfortunately, these savings are not being passed on to households just yet, because we have the retailer sitting between the wholesale and households. But through different conversations with the industry, we're really encouraging retailers to offer cheaper daytime tariffs so that people can actually benefit from more and more solar in the network. And we have seen a couple of retailers actually started providing free daytime electricity. In Queensland, a couple of examples in New South Wales, so it's becoming more and more popular. So this will, by default, encourage people to shift more and more demand into the middle of the day. If we can increase that demand, then perhaps there is not much need for curtailing and stopping rooftop solar from generation. We found that the associated emissions with water heating was reduced around 14.3%, and this highly depends on the state and the renewable energy mix there. And if we could roll out successfully across the NEM, 2.3 megatons of CO2 per year could be reduced. And basically the financial wholesale arbitrage changes across different months, depending on the wholesale market price and other generators. We'll discuss about the voltage impact on the network. So as we increase the load in the network, we're seeing local drop in the voltages. As simple as this plot, you see the water heaters coming online, and you can see the blue, the voltages are dropping for that operational instant. And throughout this trial, when we look at the voltages, the reduction of voltages when hot water demand was shifted into the middle of the day, around 2.6 volts were reduced. And we've also looked at some critical meters. So critical meters experience voltages above 250 volts regularly. That meant that they had risk of curtailing their solar systems regularly. And for these households, the voltage drop was even more, around 3.4 volts. So that could really help with reducing the amount of rooftop solar curtailment. And we've also looked at, from an entire fleet level, the hot water operation and the voltages. And you can see when the hot water systems are coming online, we see the 95th and 99th percentile of average voltages are really dropping for that specific region of operation. We've also done some network power flow modeling. We wanted to look into the cases where, okay, what happens if people buy more heat pumps in the future, which has lower power rating? What happens if they stay with resistive systems? What happens? There's a bit of mix. depending on different solar ownership. So we try to come up with strategies to create a smoother and efficient voltage management. And through different simulations, we see that this is possible, and we've modeled different scenarios of solar and hot water ownership. So there is a lot of potential of using the flexible demand of hot water in managing voltages as well. One final piece with this large trial, we wanted to see the electric demand forecasting for this aggregate hot water demand. So we have tens of thousands of hot water systems. We wanted to see how accurately we can forecast the next day demand. Now there is a very strong correlation between hot water energy demand and the ambient temperature. This is no surprise for two reasons. When the weather is cold, firstly, there are bigger losses from the water tanks, so it takes more energy to heat them. And people also love to shower more during winter to get warmer. So the correlation is quite obvious, and there is a slight lag as well due to the thermal mass of the tank and the houses. So the good news is we can very accurately forecast the aggregate daily demand of electric water heating energy. And not only on the aggregate level, but we could also forecast at the substation level with high R2 square as well as really low mean absolute percentage error. And one final piece here for the more on the behavioral side of things and consumer social science perspective. The retailer partner has carried out a survey with 18,843 customers participating in a trial, and only a very small percentage of them actually gave them a call saying we're having problems with our water heating system. So the trial from that angle was quite successful, and opt-out rate was 0.3%, so it was quite low. So more detailed surveys were carried out, and from a couple of the participants we found out that as long as they didn't change their routine significantly, the trial was successful, and this new way of operating water heating systems, shifting them from nighttime to daytime, didn't cause any disruptions in their regular daily life. Okay, so now we're moving on to some thermal modeling results. I'm aware also we have less time than allocated, so I might rush through this a little, but happy to take any questions if you have. So what we've looked so far, water heating systems in aggregate, we have tens of thousands of them. Now what we're looking here is the water heating systems at the household level, and we want to understand the thermal dynamics, thermal behavior of these systems. In this project, we've looked at different technologies, resistive heat pumps, gas heaters. Quite a few of us have gas systems. Instantaneous ones as well as the storage. We also looked at solar thermal collector. We wanted to consider the effect of household behavior, whether you are a working family, whether you're retired, whether you're a night shift worker. So we've modeled different water draw profiles, and we've also done this analysis for different states, for different number of people and different network and retail tariffs, as well as different control strategies, the older control, the new control through the network companies, a solar soak only component, which our aim is to really get most out of excess solar, so limiting the water heating just to the solar soak periods. Now I'll just summarize the key findings. One of the key findings, what we found, Transys modeling, which is an industry standard for thermal simulations. This modeling was also used when we have written the Australian standards relating to the water heating operations, have actually shown us that the efficiency, the storage efficiency, so how we're defining the storage efficiency, the amount of energy we get out as useful water heating energy divided by the energy that we put in is around 67 to 72%. So you can see that there's a significant amount of energy being lost due to thermal losses. So when we think about this, we know around 6 kilowatt hours is average electricity usage from an Australian household attributed to water heating, 2 kilowatt hours of that is being lost to ambient. And as you might know, if you are living in a freestanding house, you have a water tank that's outside, its insulation might not be as good. So it's like turning your kettle continuously on and keeping its temperature high and losing lots and lots of energy. So that's an analogy there. So it can represent 10 to 15% of one's electricity bill, depending on the usage and tariff. So this is an important finding. We've also classified different losses across different states and different type of control loads and usage patterns. So one key feedback here to our standards body, it's 4692 AS New Zealand. This standard is minimum energy performance standards for water heating tanks, and it's from 2005, and it hasn't been renewed or revised since then. And we are now living in a different energy landscape, and we believe that there might be some motivation to actually go back and see if we can actually improve this. What we've done is when we improve the heat loss coefficient, so if we reduce the heat loss coefficient by half through improved insulation, you can achieve 15% savings. However, we need to do a more detailed cost-benefit analysis. How much cost increase this is going to cause on customers? Can actually the manufacturers fit same amount of water without necessarily modifying the tank significantly? So there is more work to be done, but significant potential for minimizing heat losses. We've done the similar thermal modeling for heat pumps. And we wanted to look at their annual coefficient of performance. So that's a term used for their efficiency. Heat pumps have coefficient of performance around 3 to 5, depending on the region and the quality. That means you give one input of energy and you can get 3 or 5 due to the refrigerant and being able to use the latent heat in ambient air. We were able to look at how coefficient of performance and heat losses change for heat pumps based on these variables that we've discussed. And annual emissions, when someone changes to heat pump from a resistive heater, you see 67% of reduction of their emissions. And obviously the NAM region plays an important role. For example, South Australia with very high renewables has 20% of emissions that you get in Melbourne due to water heating. So that would also depend on whether you are using your solar soak, solar consumption, or importing from the grid. We've also looked into, we forecasted the aggregate level of water heating demand. Can we actually forecast the individual household level water heating demand? Most of these water tanks do not own a water flow meter or a thermocouple, so they're like a black box. We only have their electricity measurements, so we don't know much about them. And therefore, we try to generate lots of different scenarios based on how many people are in the house, based on weather, based on different user behavior. And we try to estimate the state of charge of the tank. So we have approached from a probabilistic point of view, and we try to create a distribution of, based on different scenarios, what is the likelihood of this household's water tank having certain percentage of state of charge at this time of the day. So we are trying to create some probabilities here. And based on different usage profiles, whether you're using only morning and evening, whether you're using it throughout the whole day, and based on different number of hours of heating and the starting time, we've quantified the risk of running out of hot water. And this is especially important because our ambition is to shift as much water heating demand into the daytime. And we've looked into cases, what happens if we entirely shifted the water heating demand during the solar periods? Does it ever cause any risk to you? What if your in-laws came? What if your friends came over for a long stay and your water consumption went up significantly? And so what we recommend is to include water heating windows early morning and late afternoon, and that really minimizes the risk of ever running out of hot water when you are on the solar soak only water heating strategy. Okay, we're running out of time. So we have basically summarized all these outputs into an online-facing customer hot water roadmap tool. And in this tool, household owners can basically go type in their address, postcode, how many people are living in the house, what sort of water heating technology they're using, and they can get an estimate of potential savings with different water heating technologies, emissions reductions, payback time, etc. And we consider lots of different scenarios, including different capital cities. Now we've extended to different postcodes actually. Do you own a PV system? What sort of tariff you're on, etc. So this tool basically compares resistive systems, heat pumps, solar thermal gas, instantaneous storage. If you have an electric system, do you have a PV? Do you don't have a PV? What sort of control strategy you are on? So we can quantify your annual water heating energy costs. We can quantify the net present cost if you're having an investment over a 10-year period. That includes the initial cost, maintenance cost, relevant rebates, etc. And the payback period if you wanted to shift from, say, resistive to heat pump for your specific case, how long does it take to pay that investment back? A couple of screenshots from this tool. So on the left, we have a household from Sydney with 4 people. They use the water during morning and evening mostly. They have solar system, and so basically we're comparing their current system to a potential new heat pump and looking at their estimated bills. On the right-hand corner again, we're looking at different scenarios for a people with 4 people in Sydney based on different usage patterns. How do their annual costs, their distribution may be based on the different technology types. And there are lots of different comparison options in this tool. Final section, I'll summarize our contributions through this research. We have got some exposure on media. Various channels have published our research and the findings from them, which was a good contribution. Australian Energy Market Commission, actually our projects have informed their flexible trading arrangements through quantifying potential financial and environmental benefits of the flexible demand. And we have had various consultation processes and were invited to various different seminars, Energy Efficiency Council, AEMC, REEM, Steve Eltron, and some more there. And finally, we have 2 key project reports that are online. We have this online tool that is available. We have an open source GitHub repository. If you wanted to replicate, if you wanted to work this tool in different applications, it's available. And we also have 2 articles, journal articles that are under review. And some future research directions, and then we're done. So we would like to continue improving the online customer hot water roadmap tool. We would like to see the expansion, the rollout of this electric water heating to different states and different DNSP regions. There is some room for improvement for controlling heat pumps, as I mentioned. We would really like to take these findings of thermal performance and inform Australian standards to hopefully update our relevant standards in this space so that it will bring energy savings to users. Thank you very much for listening, and happy to take on questions if you have time.
Thanks, Baran, for a very different talk in the normal SPREE series of talks. Notable takeaways from me very quickly. Large-scale solar farms out there, 30% curtailment. We can work as hard as we like on improving efficiency by a few percent. But we lose, the farms themselves are losing 30% of their output due to curtailment. So we need to shift the load. And then when you shift the load to heat your hot water, you're losing 30% of the energy just in inefficient processes. So there's loads of ways we can improve the processes. And it's great to be looking at it in that level of detail. Any questions? Comments?
Maybe a quick one, Baran. Great presentation. Just that curtailment of 30%, is that split into load balance and operational, or is it network restraints plus load balance?
Yeah, mostly economic, but also includes some technical curtailment as well. Yeah, so it includes both of them.
So most of that can be reduced through consumption of...
Yes, so they're curtailing economically. That means they don't want to pay to generate electricity. Yeah, that's right. So if we had higher demand, they might as well actually be able to generate, yeah.
So I think the point is the electricity price goes negative, right? So you have to pay to
Yes.
export,
Yeah.
right? So they choose not to. Yes, so demand is going to help.
Yes.
Yes. And Australia is at the leading edge of this because we have more solar just about per capita than anywhere else in the world. We certainly have more solar energy generated per capita than anywhere else in the world. So this is leading edge. And analysing and understanding what's happening with our networks and how we can change our behaviours, we get to set the pace.
Yes, that's right. No, okay, cool. I thought Anna had a point. Yeah.
Baran, what are the key barriers, do you think, to harnessing more of the opportunity for flexible hot water?
What are the opportunities? Yeah.
Or the barriers?
Barriers, yeah. Good question, Anna. So one of the barriers, in my opinion, is that, first of all, there are two ways we could really harness that. Households can invest in a technology like a timer or a diverter. They pay money and then they install it behind the meter, and this could achieve practically this flexible demand shifting and harnessing excess solar, but it includes capital cost. And some households have already done it. As I said, the previous 25% of the control load has already gone down that path. In my opinion, if we wanted to have flexible demand controlled by aggregators and networks, we really need to offer some financial incentives to the households. So free or very low cost energy in the middle of the day, let us control your water tank, and then we'll give you a very financially rewarding tariff, and you will heat your water for practically very low cost, almost free. And I think that way households will have more incentive to join this new smart meter control. Yeah.
And I guess historically, off-peak hot water is really the best use case, where it was we had excess coal-fired generation at night, so people were incentivised to go off-peak, and now the off-peak period is in the middle of the day.
Yes.
And it's one of the few cases I think that's been really successful in motivating consumer behaviour.
Yes.
Everything else seems to have been small projects rather than a really big outcome.
That's a really great point, Renata, and that's something that I forgot to mention. That whole nighttime water heating was to keep the coal generators online, also reduce the peak demands, which has been one of the most significant challenge for network operators. But as we move into the future, minimum demand is becoming also a very serious challenge. So we really need some strategies to mitigate and help networks. And I think, the flexible demand is important from that angle.
I have one more question. So the risk analysis where you looked at the Monte Carlo simulation, where you're looking to avoid people running out of hot water, have you taken into account those findings into your research, like the emissions reduction and so on? Was that included? Or?
So we do include some level of fluctuation, so we don't think things stay static. So the daily liter consumption changes in that tool. Yes, there is some normal variation that takes into account, but we don't change the behavior in that tool. So if you tell us what's your dominant, like if you're a working family, we take it as you probably use more hot water in the morning or in the evening. So that's the thing that we keep it as a more...
So if a household were to take your advice and preheat, or they would heat their water a bit more in the mornings and the evenings, as you're suggested in that Monte Carlo simulation, that's a potential change in behaviour, do you think, if households were to switch their heating to the middle of the day as opposed to control load, for example, or just heating whenever they need it?
Yeah, sorry, let me clarify. We get that from as an input to the tool. So we ask you, what is your most prevalent usage of hot water in the house? And we don't necessarily tell them to change their behavior, but we give them various different analysis based on that behavior. But perhaps that could be another output we could suggest.
I wonder if there might be a change in behaviour based on if they did switch and they started to preheat or they heat in the morning and the evenings, and how that might affect emissions and
That's a great suggestion. We give them, like for example, if they shift to heat pump, what would be their saving? And we could also give them other advice with their usage patterns. Yeah. Thank you.
Okay, if there are no more questions, I'm going to finalise with a couple of comments. One is that these reports and this data is available on the CEEM website. So I think if you looked up CEEM, CEEM, you would be able to find all of this and more, including access to GitHub and this other platform, the solar hot water heating platform. So you can go there. And if you, in addition to Baran's talents in that you've seen here, he's also one of Australia's leading talents in the hand pan. So if you want a diversion, you can go and look him up. Baran Yildiz hand pan performances. So.
Thank you, Renata. I won't put those links there, but we'll definitely include the CEEM.
You have to look for that somewhere else.
CEEM links under the online recording. We'll put the reports and the tool as well as the repository there for sure. Yeah, thank you.
So thank you. Join me in thanking Baran for this great presentation.